All right, everybody. I am going to start things off here, and then we'll have John chime in. We have a presenter today, Ted Vergis with enVerid Systems. John, are you there?
Yes. So, hello, everyone. I guess my job mostly is just to introduce Ted. He's going to do most of the speaking, and so I guess I'll do that. Here is his bio. He's been with enVerid for 3 years. Before that, he's had 10 years of experience in energy efficiency, storage, and renewables. He worked for Tesla and Sunrun. He's actually been responsible for about $1 billion in construction projects. So that's pretty darn good. He's responsible for all sales at enVerid in the US and Canada. Okay, so but here's where it gets interesting. He is an honor medal recipient, and I never really heard of that. But what that means is he saved a couple people's lives. That was kind of neat. He's a ex-pro surfer. He's got a bachelor's in science in business with a concentration in sustainable management and sales from Cal Poly out here in San Luis Obispo. That's where we are. He now lives in LA. Anyway, enVerid is an air scrubbing technology that removes all ASHRAE 62.1 contaminants from indoor air with no byproducts. They use sorbent materials, which I don't know what that is, but Ted does. I guess they deal with LEED, they deal with value engineering to reduce HVAC capital and operational expenditures, and they deal with ASHRAE 62.1 compliance all over the world. Anyway, that's my introduction. Ted, you ready to go?
Excellent. Let's get down to it. Thanks so much for that introduction. I believe the congratulations is in order. I think this is officially the 2nd year anniversary of you all doing these webinars. So thanks very much for having me on this session today. Great to see some familiar names on the attendee list here. Without wasting too much time, very excited to introduce to you all the ASHRAE Product of the Year for 2019 and introduce what sorbents are. I see some familiar names on the attendee list, so let's get right into it here. John, can you guys see my next screen here? Is that sharing all right?
Absolutely, it's working good.
Fantastic. We're in business. So as an agenda today, we're going to talk a little bit about ASHRAE 62.1. What is it? What are the different subsections within 62.1 that you can use to reduce outside air and be fully compliant? We're going to talk about enVerid a little bit as well and how you can use sorbent-based technologies to scrub indoor air, essentially turning buildings into more or less submarines, right? Where you're recirculating indoor air as opposed to having to draw in a huge amount of outside air to condition that building. We'll talk about some design integration, some use cases, and some case studies as well. Really what I'd like everybody to take away from today is how the indoor air quality procedure differs from demand controlled ventilation, where you're putting sensors in individual spaces, and ventilation rate procedure. We'll talk a little bit about the changes to 2019 ASHRAE 62.1 that are particularly relevant. We'll talk a little bit about applicable lead points for deploying the indoor air quality procedure. Many folks on this phone call might be familiar with the fact that you can get 1 lead point for increasing outside air versus baseline by 30%. Well, by actually reducing outside air by up to 60%, you're eligible for up to 12 lead points on new construction and up to 17 lead points on existing buildings. So it's a huge, huge lead point generator here when you're looking at the indoor air quality procedure. And then we'll talk about compliance a little bit. There's a little keynote there for California. We'll talk about first cost savings and utility rebates as well. So hopefully this is very relevant for everybody on this call, and away we go. So ASHRAE 62.1, just for those who might not be really wonked out on ventilation requirements for large commercial buildings, there's essentially a few different procedures that are done to calculate how much outside air you need to bring into a building. The one that most folks are familiar with is the ventilation rate procedure. It's a certain number of CFM based on space type, occupancy, square footage, etc. There's nice tables in ASHRAE that show how much outside air you should bring in, and then that is used to flush out contaminants from within the building. A subsection within the ventilation rate procedure is demand control ventilation, and basically what this says is if occupancy varies within the space, you can place CO2 sensors within those areas. And when the space is not as densely occupied, you don't have to bring in as much outside air to ventilate the space because you're not flushing out the people component of those contaminants. The lesser used and relatively unknown until a few years ago was the indoor air quality procedure. This has actually been in the standard since before 1981, and it's also referenced in the International Mechanical Code 403, IMC 403, where you can use an engineered system, air cleaning strategies to reduce the amount of outside air required. And what enVerid does with our engineering partners is we're actually able to reduce outside air in many cases all the way down to just building pressurization. So the only outside air requirement is the outside air that you need to pressurize the building to overcome toilet exhaust and other things like that. And that enables you to see massive energy savings because you're not having to condition outside air that's under non-ideal either humidity or temperature conditions. So let's talk about ventilation rate procedure and demand control ventilation, which many folks are currently using today. Ventilation rate procedure often leads to unnecessary energy consumption. You're prone to overventilate with VRP, and it also doesn't control for outdoor generated pollutants. So for those of you who are in California right now with the wildfires and things like that, if you've got LEED buildings out there that are, subscribed to the ventilation rate procedure plus 30%, they're sucking in potentially huge amounts of outside air that have smoke and ash and all kinds of particulates, PM 2.5 in them. If you're designing buildings next to roadways, you're sucking in carbon monoxide and other roadway emissions and particulates. So ventilation rate procedure might not be dilution within buildings, especially in polluted areas, maybe Colorado, where you've got higher ozone levels outside. You can't ventilate out ozone. So ventilation rate procedure might not be the best path to go. And there's some changes in 2019 ASHRAE that actually specifically call that out. So stay tuned. Demand control ventilation also doesn't control for outdoor generated pollutants. It also doesn't account for pollutants generated indoors that are independent of human activities. So there's many literature documents, many studies that indicate that formaldehyde, TVOCs, and radon are not addressed by demand control ventilation. They also require CO2 sensors for each ventilation zone. Those sensors must be calibrated frequently. That calibration metric there is actually changing in 2019 ASHRAE as well, so we'll talk about that. But you have to calibrate those sensors. That's expensive. That's a big time maintenance item for facilities teams. And then for certain spaces such as offices, portions of ventilation related to people component is low. So that leaves you very little margin to save energy using demand control ventilation in many cases. Here's an example of how ventilation rate procedure, demand control ventilation, and the indoor air quality procedure might break out on a standard, let's say 20,000 square foot building. If you're ventilating according to VRP in the ASHRAE standard calculations and tables, you might be required to bring in 2125 CFM of outside air. If you apply CO2 sensors to each of the spaces, then you can drive down that outside air. You can modulate those outside air dampers down based on the people component within that space. But that eventually hits a floor, and that floor is about a 30% reduction in office buildings versus ventilation rate procedure. The indoor air quality procedure, as long as you're able to scrub for all the contaminants being emitted within that space, CO2, formaldehyde, ozone, etc., you can actually drive that outside air down, in this case, down to 652 versus that original 2125. So significant outside air reduction versus demand control ventilation. Now, I mentioned some of the addendums that are now published for 2019 ASHRAE. So for demand control ventilation, this is a brand new addenda here, which basically says that where CO2 sensors are used for demand control ventilation, the manufacturer has to now certify that they're accurate within plus or minus 75 ppm at a 600 ppm and 1,000 ppm concentration. So that's on the manufacturers. You're going to need to validate that if you're designing buildings with demand control ventilation. And no longer can you not use sensors that need frequent calibration. These sensors have to be manufacturer certified to not require calibration more frequently than once every 5 years. Very few sensors on the market for demand control ventilation right now meet these two requirements. So be very aware that for ASHRAE 2019, these are two new requirements that are very constricting for demand control ventilation, okay? For ventilation rate procedure 2019, this is a big change. The indoor air quality procedure amongst the engineering community was not used for quite some time. Number one is there weren't a lot of products out there that could address the full list of contaminants that had sufficient testing data around their ability to remove contaminants. And there was also some lack of clarity around which was the quote unquote safest methodology to use within ASHRAE for 62.1. And what's interesting is that many engineers defaulted to the ventilation rate procedure, sometimes using demand control ventilation, and very rarely use the indoor air quality procedure. Now, with a lot of the new devices on the market, like enVerid, we're able to address the full list of contaminants. We have ASHRAE 145.2 testing for efficiency on those contaminants published. And one thing that's interesting is that ASHRAE now recognizes that outside air is frequently polluted. You know, ASHRAE is a multinational organization now that it's worldwide. There are environments where ventilating according to the ventilation rate procedure is not actually ideal. So ASHRAE 2019 actually clarifies that if you are designing a building where contaminant sources and source strengths are not typical of the occupancy, so I'll give a couple of examples. An unusual source is an item or activity that could create or emit contaminants that occur rarely within an occupancy category. So I mentioned earlier designing buildings next to roadways, next to airports, etc. Those create or emit outdoor contaminants that occur rarely within an occupancy category. So for those sources, if you're designing a building there or have a building there, you actually must use the indoor air quality procedure according to ASHRAE 2019. This is a massive change for the entire industry. ASHRAE 2019 says if you're designing a building that could nearby unusual sources of contaminants that could create or emit contaminants that occur rarely within an occupancy category, then you must use the indoor air quality procedure. Big changes. So I mentioned that the 62.1 indoor air quality procedure is referenced in the IMC 403. It basically says that the minimum required rate of outdoor air can be reduced with engineered ventilation system design, like an enVerid system, in accordance with the indoor air quality procedure within 62.1. ASHRAE 62.1 itself cites air cleaning strategies as an acceptable and actually more cost-effective method, potentially a more cost-effective method for providing good indoor air quality. You receive the benefit of conditioning less outdoor air, and also may lead to levels of perceived acceptability and higher indoor air quality. So you can use this methodology this calculation, which exists within ASHRAE 62.1, to achieve better indoor air quality than ventilation rate procedure. Big changes. So let's talk a little bit about what the indoor air quality procedure is. Basically, it addresses a full list of contaminants. Right now, that contaminant mix is 32 VOCs, 5 inorganics, and top 10 contaminants if not included in the list above. An engineer will set the concentration limits. Now, this is one part of the indoor air quality procedure, which has led to some pause amongst the MEP community, saying, I'm not a hygienist. I don't know what the concentration limit should be within a space. ASHRAE has now provided some guidance on this. You know, formaldehyde should not exceed 33 micrograms per meter cubed, et cetera, et cetera. And LEED also has published limits as well. So you can reference both of those for concentration limits within certain spaces, very similar to how you would reference other tables within ASHRAE. Then you identify an air cleaning solution and its efficiency. ASHRAE 52.2, which we're all familiar with, is what assigns a MERV rating. And then ASHRAE standard 145.2 is gaseous filtration testing. So what is the efficiency of your device in accordance with ASHRAE 145.2 and its ability to remove contaminants like formaldehyde, carbon monoxide, ozone, toluene, benzene, NOx, SOx, BTX from the air without any byproducts. You use the mass balance equation that's within ASHRAE 62.1, and this is a new process for many folks. Trust me, it's not that complicated, and enVerid does it every day for many, many projects, and we're happy to help. And then there is a verification component. Now, for this IAQ testing and surveys, frequently you can reference other similar buildings in the area, so you may not need to do an actual test or survey on that particular building if you've done it before, or other engineers have done it before in the area, and you have similar conditions. So don't worry too much about that. It's a very subjective test, and typically if you do the testing, it's one question survey, and the testing is very easy to pass as well if you've done everything correctly before. So what's this look like really? Okay, don't freak out about this formula here. We'll break it down. So basically, what is enVerid? In this particular case, an enVerid HLR, or HVAC Load Reduction technology, will be applied to the return air stream of an HVAC system. We're a side stream application, so we actually only scrub a portion of the return, a very small portion of the return, and we treat that air for all contaminants and then return that clean air back into the system's return to the air handler, and all your downstream systems can remain constant. This system design is especially useful for retrofit applications. I understand many folks on this call are from ESCOs, but basically what this enables you to do is keep your downstream air handler sizing. If you're using a VRV or VRF downstream, those can all essentially remain constant. And all you're doing is pulling a portion of the return through this device, cleaning it, and then putting that back into the system. So it's built to be self-contained. Now, how are you sizing these systems? enVerid, because we remove CO2, which is a very unique component about the enVerid solution, is we remove CO2 and all other VOCs as well. Basically, we calculate our systems according to occupancy. We know we can remove formaldehyde and all the other contaminants faster than they're emitted within spaces based on the mass balance equation. CO2 is our limiting contaminant of concern. So one enVerid HLR is good for about 150 occupants worth of design occupants. And you can apply one HLR for those 150 occupants, and you're going to end up being able to drive outside air requirements down to essentially just building pressurization. So essentially the mass balance equation is up here. We know the emission rate of these contaminants according to square footage, space type, occupancy, and decades decades of ASHRAE research. So these emission rates are published by ASHRAE. And what you're trying to do, what you've traditionally done with ventilation rate procedure is done dilution. So with the indoor air quality procedure, you're still bringing in some outside air because you have to pressurize the building, typically somewhere between 5 and 8%. So you're still bringing in about 5 to 8% outside air. And that will assist with diluting some of these contaminants. And so this is basically your original VRP calculation right here, N minus dilution. All the indoor air quality procedure does is give you one more lever to pull, which says, now we're also going to apply a certain number of HLRs, a quantity of HVAC load reduction air cleaning devices. We know the efficiency, EF, of that device on all contaminants, and we can apply that within a calculator to say, here's how efficient this device is at removing those contaminants with no byproducts. And we're setting our concentration limits, either referencing ASHRAE or referencing LEED limit standards for the indoor air quality procedure. Pretty straightforward. And what we've seen is with the simplification and with these changes to 2019 ASHRAE, engineering teams like TLC Engineering, which is big from like Tennessee down through Florida, and many other organizations are using this as essentially their base case. So this is a published third-party study by TLC Engineering. That's an enVerid unit off there to the right, about why they're moving from prescriptive to performance-based ventilation within buildings. This is a differentiator for them where they're able to provide, number one, more cost-effective solutions for their customers. Number two, better indoor air quality by doing the indoor air quality procedure with enVerid, controlling CO2, controlling VOCs, and providing first cost savings there. Now, one thing to note is that ASHRAE does raise explicit concerns regarding certain types of air cleaning devices. One may be electronic air cleaners that produce ozone or may have unintended byproducts. We don't need to spend too much time on this, but generally what enVerid recommends is really digging in on the efficiency data and the byproduct data of each air cleaning device to make sure that you're not using one that has unintended consequences as it pertains to emissions. The other is that CO2 matters in the eyes of many studies that are coming out right now. So we may all be familiar with the studies from the Navy and others that say CO2 is not harmful to your health within a pretty extreme range. 5,000 ppm, there's an OSHA study that says you can get up to 5,000 ppm without CO2 impacting negatively your health. However, there's more and more studies coming from Harvard, from University of Wisconsin, Europe, other places that while CO2 at elevated levels might not be harmful to health, it definitely impacts cognitive function and at very low levels. So you can see here that between 600 and 1400 ppm of CO2, there's a pretty drastic change in cognitive performance here. So that's something that enVerid does remove. enVerid solution does remove CO2. And that might be something that you would want to calculate is a CO2 limit within your calculations for the indoor air quality procedure. LEED references a limit of 1100 ppm for if you're going to go for those LEED points with the indoor air quality procedure. Finally, there was a lot of chatter on this article from December of 2018 and ongoing into this year about how New York State and indeed California as well bans certain electronic air cleaning devices. What's fortunate is that enVerid is a sorbent-based air cleaning device, so we're not doing any type of electronic air cleaning. It's basically just a big filter, which all of us can very well understand much better. So keep your eye on electronic air cleaning and whether or not they're banned in certain territories, whether or not they create reactive oxygen species like ozone, hydroxyl radicals, and others that can actually produce ozone and are generally discouraged in many states. Okay. Moving on from that was kind of the policy section a little bit. It'll continue to come up throughout the session here. If you have questions, I'd encourage you to type those questions out in the chat window. We'll be handling those questions at the end of the call. So if questions have come up regarding policy or regarding the product, happy to answer those questions. You should have a chat window off there to the right for the go-to meeting. Just a little bit about enVerid. I've only been with the company for about 3 years, but we've been doing this commercially for about 10 years. The headquarters is in Boston. We have over 60 patents on this sorbent-based device. You can see sorbent granules off there to the right. Those are the sorbents that we subjected to ASHRAE 145.2 testing to certify no byproducts, no ozone production, etc., and to ensure that we knew the efficiency of our device for that mass balance equation. enVerid has units deployed worldwide. We have airports in Singapore. We've done projects all over the Middle East and Europe and France and India. And our highest density of applications is indeed in the US South and East Coast, where humidity and really hot temperatures really impact building design. Anywhere where you end up with outside air conditions or economizer mode not being used as frequently, this is a great application to see energy savings and also utility rebates as well. The enVerid solution is actually eligible for utility rebates based on energy savings from outside air reduction. So we talked a little bit about the integration here. You can see the enVerid box, the enVerid HLR off to the side there. It's a 2 foot by 4 foot by 6 foot box. It can lay on its side or be oriented vertically as well, and is a side stream air scrubber that continues to remove all contaminants of concern. I mentioned earlier that we're the ASHRAE Product of the Year. In 2019, we received first place in the green building category and received Product of the Year in all categories. And ASHRAE stated that particularly we won this by safely removing all molecular contaminants, including CO2, formaldehyde, and a full range of VOCs from indoor air, which was a big accelerator for us. We've also got DOE validation as well. The DOE has spent several years monitoring our systems with CTs to verify our energy savings. We typically see 20 to 30% energy savings on HVAC systems and total outside air reduction between 60 and 80%. And that's been validated by the DOE. They looked at our installations in Miami, in Arkansas, and other installations across the US for that validation. So what is the enVerid HLR? Basically, our goals are to show first cost savings versus demand control ventilation or energy recovery. Under ASHRAE 90.1 and the energy cost budgeting methodology, you can actually frequently eliminate your energy recovery requirement by incorporating the HLR. And that's because essentially from a technology standpoint, we're essentially 100% efficient energy recovery vehicle. So that's pretty interesting. And we're also driving outside air minimums typically below that 5,000 CFM of outside air requirement in many buildings to reduce the energy recovery requirement as well. I mentioned the LEED points as well, LEED and ASHRAE approved, and significant third-party testing as well by ASHRAE and others. We have a pretty big list of customers here. Lots of engineers are using our product across the country. Lots of organizations like Harvard who are publishing studies on CO2 are implementing our solution on their campuses and very focused on indoor air quality as well to ensure their employees are happy. We currently have over 140 MEPs designing in our system actively right now on new construction projects across the US. So we have three units here. We've got a rooftop unit there off to the right, a little bit more robust of a design just to handle extreme weather. And then we have a enVerid HLR 14M and 15M. Okay. With respect to those devices, they're pretty similar, same dimensions. Two applications are for indoors, one's for outdoors. Basically, we just have one for ducted return air and one for plenum. The plenum return has one inlet versus two. So let's get into what's inside the box. And what's enVerid working with here? So each of our units that treats about 150 occupants of CO2 and the corresponding square footage has 12 cartridges filled with a sorbent. These are granules treated with a polymer that's able to absorb contaminants. 12 cartridges. Each cartridge weighs 10 pounds each. So if you think about it, we've got 120 pounds of sorbent treating 150 occupants and the corresponding square footage for indoor air quality, removing all VOCs and CO2. We draw air into the unit past this little pre-filter here. There's two little 120 watt muffin fans here at the bottom to help overcome the unit's own internal static pressure. That air flows over these cartridges here and then back into the return air. Okay, we have a controls board to interact with the building's management system, the BMS. We also have a wireless card here as well to transmit air quality data and modeled energy savings, as well as unit status and operation to the enVerid cloud. All of this wireless component and information on indoor air quality, that's included in the annual cost of cartridge changeout. So you do have to replace these cartridges once a year. Okay, once a year is manufacturer spec. It's basically the same as changing a filter on a building. And the cost of that typically is the equivalent of around 25 to 30% of the average annual energy savings that you're achieving. Usually that can be calculated by the fact that each one of our devices reduces outside air by 2,000 to 3,000 CFM. Okay, so you can apply your kWh rate or your cost of heating or cooling energy per CFM, and then kind of back into those numbers there. Typically, we hear numbers somewhere between $4 and $8 per CFM cost of heating and cooling air. So if you're reducing 2,000 to 3,000 CFM at $4 to $8 per year, you're looking at $8,000 to $12,000 worth of savings potentially in many regions. It varies region by region. We also have a little heater on this unit. Basically, these cartridges have the ability to regenerate themselves for air cleaning capacity. So we'll get into that a little bit more later, but I wanted to show a snapshot of our ASHRAE 145.2 data here. What's interesting is that this is a real test that we did with the Research Triangle Institute, a third-party 145.2 testing site on ozone, where you do a single pass efficiency test on ozone within a chamber against your sorbent. And you can see that regardless of elevated concentration levels or time, our efficiency remains constant on anything on a part per billion level. So anything on a part per billion level for ozone, formaldehyde, et cetera, we're scrubbing consistently at the same efficiency. And here's some snapshots of our efficiency numbers here for our ability to remove these contaminants. Now, these sorbents, we didn't create these sorbents. We just found a way to do it very cost effectively for you. We licensed this technology from MIT and USC. And basically what we're doing is we're removing CO2, formaldehyde, benzene, ozone, et cetera. You'll see down here, this says radon as well. We do have the capabilities to remove radon. However, for liability purposes, we do not advertise our efficiencies of that, nor is this a radon treatment solution. But if it was applied in a radon application, it's possible that you could see some benefits there.
Hey Ted.
Yeah, go ahead.
This is John. I got a question about efficiency. Maybe you were talking about it and I wasn't listening, but we're so used to efficiency having to do with how much energy you get out of the electricity and all of that stuff. And this isn't that at all. Can you explain what efficiency means again, if you've already done it or for the first time?
Yeah, so efficiency for us from a contaminant perspective is the single pass efficiency rating of our ability to remove contaminants as they cross over our cartridges. So for example, if you challenged our device with either 100 part per billion of ozone or 1,000 part per billion of ozone, we're going to remove that ozone at 70%. So it would go down to 300 or 30. depending on how much is in the air. So our efficiency remains constant. So with CO2 on a part per million, if 1,000 part per million of CO2 is coming into our system, we're removing that at 57%, and 430 is coming out the other side.
That's perfect. Thank you.
Excellent. Thanks so much. So just going over the airflow patterns here, basically you've got those 2 muffin fans in there. You've got the 12 vertical V-bank cartridges as well, and putting that clean air back into circulation. We're removing all these contaminants, including acids, with 0 byproducts, okay? Now I mentioned the regeneration process. CO2 is so prolific within buildings and indeed the environment that eventually it will saturate our cartridges. So just as a precautionary measure, typically on a daily basis, we will put the unit into standby mode, okay? Typically when the building's not occupied, or if it's a 24/7 application, we'll do it during times of low occupancy, or we'll operate on a +1 methodology with 2 devices where one's regenerating and one's still operating. And we will essentially heat up these cartridges to 130 degrees Fahrenheit using this small 5.5 or 6.5 kilowatt electric pulsating heater here. And when we do that, actually, the cartridges release the CO2 that's been trapped in the cartridges. And we release that out through the toilet exhaust or directly outside the building. And that restores the unit's ability to absorb CO2 at its original efficiency and full capacity going forward. And so typically that occurs once a day for about an hour. And we are just regenerating these cartridges, releasing the total amount of CO2 that we're absorbing. These cartridges are so efficient at removing CO2 they can actually change weight throughout the course of a day. So in order to ensure that they have enough capacity to remove CO2, we heat them up to 130 degrees Fahrenheit and then exhaust that outside the building, okay? Very interesting. This is what makes our product incredibly unique, is our ability to consistently remove CO2 and other contaminants without having to replace the cartridges very frequently. Just once a year cartridge change out as manufacturer spec, and you're still cash flow positive from an OpEx perspective, generally. So let's take a look at just a really quick real life example here. This is the Harvard campus with Siemens. We did this project with Siemens in Boston. Basically, you have 4 HLR modules here in a mechanical room. They're all in parallel, treating the same return air. We're running that return air through the unit, placing that clean air back into the system, and then we're ducting that exhaust to the toilet exhaust for that once a day time where we go into regeneration for about an hour. And the net result here on this retrofit application was 24 tons of cooling reduction per HLR, and about 4,500 CFM of outside air reduced per HLR as well. So massive energy savings, massive utility rebates here, and phenomenal air quality as well for the 700 to 1,000 occupants within this space. Okay. You can see unducted down here. We have this damper as well. We're actually able to use mechanical room air for that purge cycle when we're exhausting out that HLR exhaust. We're scrubbing at any given time about 700 to 1,000 CFM through each unit, okay? So these are 700 to 1,000 CFM units. They can treat, 20,000, 25,000 CFM air handlers because we're a side stream application. We're not scrubbing 100% of the return. And when we purge these units to keep the building from going negative, we just exhaust that air at about 250 CFM, okay? So it's a slow bleed purge when we're going through regeneration. Okay. So again, what's also nice about enVerid is we're not one of these black boxes where you can't tell what our actual efficiency is. We're not just a set it and forget it type organization. So we've loaded this thing up with sensors for total VOCs, CO2, temperature, pressure, humidity. We can actually remotely troubleshoot most of our systems using that remote cloud, okay? And all these systems are communicating to the BMS. Let's talk about a quick application here. Now, I know many folks here are not mechanical engineers. Many folks might be in other fields, but I just want to talk really quickly. We get frequently asked how you would apply this to a 100% outside air system. So 100% outside air DOAS system here, the proposed case on the left here. where you're drawing in 15,000 CFM of outside air. We've got energy recovery treating toilet exhaust and general exhaust. And then there's 15,000 CFM of supply air. Pretty standard building, okay? So you say, Ted, I don't have a return because I've got a DOAS system. How would I apply this? You say basically what you do is you decouple this general exhaust and create a return out of it. We would scrub a portion of that return. Okay, so in this case, you've got 8475 return air. We're going to scrub 1,000 CFM of that, place that 1,000 CFM of clean air back into the return right before the air handler here. You no longer have a 100% outside air system. This is now no longer a DOAS, a dedicated outside air system. This is what we call a DCAS, a dedicated clean air system. Okay, this is a new acronym for you. By scrubbing this air, you can reduce your outside air requirement from 15,000 down to 6,500 CFM, and your supply air remains constant, so you can continue to take advantage of economizer modes. So your fan sizes will stay the same size, but you can downsize all the rest of your cooling and heating capacity if this was a new design construction. See that happen quite frequently. Energy recovery in this case could potentially be eliminated under the ECB method. We're not below that 5,000 CFM number here, but your system should be efficient enough for you actually to completely eliminate energy recovery because it's only treating toilet exhaust at that point. Okay, we have a full design guide that goes through about a dozen different integration scenarios. So if you're interested in learning more about this scenario or others, we can provide that information. And all this information is quite available. We offer tons and tons of free support because we know that many folks have never done IAQP before, or maybe never designed in enVerid HLRs before. So we offer on-site startup and commissioning assistance. We offer device specifications, CAD files, Revit files. We'll do IAQP calculations for you. We'll train you on how to do IAQP calculations. We have engineers on staff who all they do all day long is assist MEPs and others on how to integrate in the enVerid HLR system. So we're very heavy on the support side because we know that if we help you deploy these systems best, then you're going to use us again. And this is a snapshot of one of the reports that we provide. We take a look at the building square footage, occupancy, how much outside air you'd normally need under ventilation rate procedure. We take a look at exhaust because that will limit how much outside air we can reduce. And then we're able to tell you how many HLRs are required to reduce that outside air by a certain percentage. We show the calculations. We show our air cleaning efficiency on all the contaminants of concern. And then we provide a schematic in terms of how to design this in. So that's an example of a sizing report that we offer to all of our projects. I mentioned LEED. So the LEED pilot credit that I've been referencing is EQPC 124. It's a pilot credit for reducing outside air. It's very focused on health. We are very familiar with this pilot credit. We actually got the first one with the Southwest Florida Community Center in Fort Myers, Florida. They received 7 LEED points. The HLRs did not cost them anything additional because it was a new construction project. They were able to downsize their energy recovery vehicles and pay for HLRs by doing that. And they received 7 LEED points there, which was absolutely phenomenal. In other markets, we've seen projects pay for themselves on a retrofit application in under 3 years, sometimes as little as a year, based on the utility rates that are the utility rebates that are available as well. I mentioned cloud integration here, so we do have the 3G, 4G connection showing unit status and whatnot. We also integrate with the BMS system. If economizer mode is on, we go into standby, and we're typically running during the traditional run hours of a building. So all those set points are available from our support tools as well. And this is a snapshot of the SCADA, of the actual reporting that we have, so you can see whether or not units are running, energy savings, modeled energy savings, as well as CO2 and total VOC outputs as well. Okay. So where should you apply ASHRAE 62.1, the indoor air quality procedure? Office buildings, colleges and universities, K-12, malls, big box stores, green and LEED buildings. Not good applications for us are anything that has high exhaust requirements. So hotel guest rooms, hospitals under ASHRAE 170, and kitchens. Now that said, we don't have to treat the whole building. So a hotel might have a big conference area. We can treat that if it's on a different zone. Hospitals frequently have administrative wings that have different ASHRAE requirements. We can treat those. We might not treat the kitchen, but we could treat the cafeteria. We also do a lot of work with like WeWork and Regis and other tenant fit outs where you might have a singular floor with its own mechanical room where they need increased occupant density, but might not be able to get that because the building's HVAC system can't be expanded cost effectively. So by placing us on that floor, you can get increased occupant density, okay? Also take a look at applications where outdoor air is in non-attainment or polluted, or where contaminants of concern are high outside. This will enable better indoor air quality by driving down outside air requirements. Buildings also in hot or humid climates are also great for us, okay? Now I wanted to show a quick case study here. I know we're about 45 minutes in. We're just gonna go through a couple of quick case studies, but this is from Spectrum Energy, a third party that analyzed enVerid solutions in the DC area. They calculated loads without ERVs, where the cooling equipment would have had to be 115 tons. Load with ERVs, where the equipment sizing could come down to 100 tons, or load with enVerid and no ERV, and the cooling equipment size was able to be downsized to 95 tons. So about a 20-ton reduction versus traditional equipment sizing without an ERV, and a decent improvement versus traditional energy recovery. From a costing perspective within VAV system here, on a new construction project, the first cost was actually a little bit less, about break even with the original solution, $150,000. And then with the maintenance costs and whatnot, the total lifetime cost savings with enVerid was much higher. It was $200,000 versus $135,000 with ERV and conventional design. So phenomenal payback period on a new construction project, basically not costing anything. Marginal maintenance costs from cartridge changeouts and other service with enVerid versus ERVs, where those wheels might seize or big problems come up or they get turned off. And massive energy savings as well, 16,000 versus 13,000 with a ERV. What this enables you to achieve is a better EUI score, which is very important frequently, especially on new builds. So 51 on your conventional design, all the way down to 39 with enVerid. Another example, so that was with a VAV. With a VRV system, you're looking at a total lifetime cost savings differential of almost double over a 20-year period, and essentially an equipment cost of a marginal increase here with enVerid versus the ERV. So marginal equipment costs, but you essentially make that up immediately in the annual energy savings achieved as well. So 7,000 versus 10,000 with enVerid here. And that enables you to get an EUI score of 25, which many regions have a mandatory requirement of 50 below. Others are more stringent, but to have an EUI score of 25 is absolutely phenomenal, okay? So just re-highlighting the benefits for 20 to 40K of CapEx savings per unit is not uncommon. 3 to 10K of annual OpEx savings based on utility rates and net of the service costs as well. 10 to 20 tons of cooling capacity per HLR. You can downsize your DOAS, chiller sizing comes down, ductwork comes down, cooling towers can come down, and then also massive utility rebates in many regions is available as well. I think worth mentioning here that currently in California, which many of you are likely in along with myself, Title 24 and the mandatory outside air refresh policy, mandatory air exchange policy, number one, may not be the best for buildings designed next to roadways and polluted areas, areas with bad outdoor air quality, or in wildfire areas as well. However, currently CARB, the California Air Resources Board, and Title 24 does not have an exemption that's easily attainable for enVerid or the indoor air quality procedure. So if you have local officials that you're in close with within your region, or you're familiar with the folks up in Sacramento, we highly encourage you to reach out and begin asking questions about how you can potentially deploy the indoor air quality procedure in California without the significant burdens that are currently placed for exceptional design. They require exceptional design approvals to be done at multiple levels, all the way through OSHA and the local building code officials, et cetera. And so far, no one has made it through that process because it's so laborious at this time. So if you are engaged in Title 24 conversations, if you are engaged with the California Air Resources Board or others, it'd be really great, number one, for the planet, number two, for energy consumption and cost savings, number three, for indoor air quality. If you feel sufficiently educated on this, to begin asking those questions at the local level. So that's the only way we're going to get those things changed, is if the folks that do these projects begin asking those questions about how they can deploy a better method of indoor air quality and ventilation. Because indeed, we see in other more progressive areas of the country, like Washington, D.C., which has a carbon net zero by 2050 mandate and significant reductions by 2021, they're deploying HLRs and the indoor air quality procedure very rapidly and seeing net CapEx savings, energy savings, and achieving massive lead points as well. So this is a WeWork building, single floor. We deployed 4 modules and saw massive benefit there. Schools as well, K through 12 application, 400,000 square feet, 17 HLR modules, and beginning construction right now. University of Miami, we've done several installations with them. In this particular case, they gave us a limit of 800 ppm of CO2. They're very focused on reduction of CO2 levels to make their students' cognitive performance hopefully higher. And so by applying 40 HLR modules there, we were able to achieve very, very low limits of CO2 levels versus conventional ventilation. In this particular case, this is a building in downtown DC where Alexander Graham Bell tested his photo phone. And in this particular building, it was switching from a school to a museum in terms of space type. The mechanical rooms were too small to accommodate the dimensional size of the equipment that needed to be increased based on the occupancy increase. So by applying the enVerid HLRs, we were able to actually decrease the dimensional size of the overall system sufficiently to achieve both better indoor air quality and also fit everything in the mechanical room. So that's a big concern, right? Especially amongst architects, is adding enVerid going to increase the dimensional size of my mechanical room? And in many cases, it does not. On a retrofit, obviously, you might have to suspend it from the ceiling, put it on top of an air handler, get a little more creative with it. You can even place it directly in the space. So here's a variety of other schools in a variety of climate zones, Pennsylvania, Virginia, et cetera. This is an example of our Department of Energy testing, where a CT was used to measure energy consumption with the HLR and without the HLR when enthalpy was remaining constant. You can see the massive energy savings right there. This is a DOE study that occurred over the period of 3 years, which is phenomenal. And then you can get crazy with this as well, right? So brace yourselves. This is a 40-story, 1.3 million square foot application. This is the Morgan Stanley Worldwide Headquarters in Times Square, New York. 2 mechanical penthouses in this building, split into 2 sections each. So we had 10 HLRs here, 10 on the other side of the building. This mechanical room is an open air, it's a plenum. So it's a giant return, and unducted, we're drawing air into the units, returning that clean air back into that room, and then the fan wall is drawing that clean air back into the system. The singular duct here that you see at the top, the purpose of that is to for the exhaust cycle. Since it's a 24/7 application, we always have 2 units going into regeneration and the remaining units scrubbing the building. So you can see here that this solution can really scale up here. And the net result on this was less than a 1-year payback. We reduced outside air 63% from 190,000 to 70,000 CFM for 7,000 occupants and 1.3 million square feet. Just because we're reducing outside air doesn't mean that we're compromising on indoor air quality. In this particular case, you can see that we were reducing outside air. We saw a peak savings of about 30%, peak of over 40% rather, and total VOCs, CO2, and formaldehyde all decreased. So even though we were reducing outside air and seeing massive energy savings, indoor air quality improves. One example of this is at LSU, where one day this system actually showed a spike in VOCs, and the net result there was that we found out that they were painting with a VOC-laden paint. So we were able to specifically address with the field team real time. We were able to call them and say, hey, there's a VOC spike. We're monitoring the system. Everything's fine on our side. What are you guys doing? And they said, oh, we're painting, but whoops, we used the wrong paint. So kind of a cool application there, 40% plus energy savings. And then final case study that I'll go through here is Boston Properties. Nice little 400,000 square foot building in Boston, reduced outside air from 64,000 CFM to 12,000 CFM, variety of space types, conference rooms, cafes, coffee shops, lobby shops, etc. Massive energy savings there as well. So Abraxas, I'll turn it back to you guys.
Hey, that was really good. That was really, really good. Thank you.
Thanks.
I really enjoyed that. Hey, I have some questions. Some are mine and some are people's who are attended. I guess I won't tell you which are which. It doesn't really matter.
Fair enough.
You might have actually heard it's mine. Do you have spreadsheets or some kind of tools? Because a lot of these folks are, or some of them are going to be are PDEs, I think, or guys who actually are going to recommend this as an ECM. I mean, but how do we know what we need? It'd be really useful if you had a tool for us, a spreadsheet that we could use, or an online tool or something, so we could estimate energy savings and costs. That would be really great. Is that possible, or do you have it?
Yeah, absolutely. So I have a takeoff worksheet that asks for all the required information to get a project going. We do have an online calculator that we issue out. Typically for your first project, we'd love to do this collaboratively. So what we do is we provide all the required information. We ask you for the required information to do some calculations on the building. Then we'll go through with you the calculator to show you how the calculations work, to show how you apply the efficiency numbers and things like that. And then we also go through design integration with you as well, based on any drawings that you might have or thoughts that you might have on the project. And then once you're really comfortable with it, we'll issue you an online calculator logon so that you can begin doing this yourself. But we offer sizing compliance reports for all of our projects and offer to walk through the calculations and design integration on every single project that you have. And you can just email myself, Vergis, TVERGIS at enVerid.com. Again, that's TVERGIS at enVerid.com. Any projects that you have in mind, and we'll provide those calculators and questionnaires for you.
Okay, here's another one. Does the HLR increase the temperature of the air?
It does not. It doesn't change the latent properties or the thermodynamic properties of the air. All it is just running through cartridges. So no electronic air cleaning. We're not applying an electrostatic charge or anything like that. It's the same as running it through a filter. The only time we change the temperature of the air is when we are going into that once a day regeneration cycle to release the CO2 from the cartridges, or we'll heat our cartridges up to 130 degrees. And then we'll enable the system to cool back down before it resumes normal operation, scrubbing the return.
Okay. You know, I was talking to one of your competitors who was saying bad things about your stuff, and the first thing they really said was it's 5 to 6 kilowatts. But then you said it's only 1 hour. It's 5 or 6 kilowatt hours times what? 10 cents a kilowatt hour. It's 50 cents. So that kind of really pay off in comparison to how much you're saving. So I didn't think that was a very good argument. Here's one. So I'm going to read it because it'd be better. I'm not going to be able to summarize it. Do you ever see an increase in energy use? I'd imagine in cases like Southern California, where outside air is used a lot of times to cool the space, when having to turn on the HVAC system in order to account for any increase in temperature due to the HLR, there would be an increase in energy. I don't know if that made any sense, but that's the question.
Yeah, absolutely. So we're just heating about 1,000 CFM of air up to 130 degrees for about an hour. So that's 5.5 kilowatt hours of energy essentially for the regeneration cycle. You don't have to turn on the HVAC system or anything like that. We're just exhausting that warm air out through the toilet exhaust. And the two little muffin fans within the unit are the only other power. They're 120 watts each. That's the only power that the system's using. So like in Southern California, for example, you're going to have economizer mode a fair bit of the time. Our unit is in standby, so your system's using free heating and cooling as it normally would. On very hot days, or if you have heating days as well, our unit would essentially be just pulling return air from the building, running it through our cartridge bank, and putting that air back into the return. So no thermal change of the unit, and if anything, it should actually show really significant energy reduction savings because you're not having to heat up or cool down that outside air that you normally would. You're basically just running the existing air within the building that's already been conditioned back through the system.
Okay, so we've got, I'm going to try to get these other ones in. We've got 4 more. So here's 5 more. What percentage of return air is exhausted by the HLR?
So we're not exhausting any return air. We're scrubbing 100% of it, putting 100% of it back into the return. When we go into regeneration, we're just purging at 250 CFM.
That was easy. Okay, good. How often would the sorbent need to be purchased, or is the regeneration cycle supposed to clean the sorbent such that none need to be purchased?
Yep, so we recommend once a year. That's manufacturer spec is once a year cartridge change out. Eventually the cartridges will oxidize, so once a year cartridge change out. And other than that, nothing's required on a daily basis because the regeneration cycle is actually what's regenerating the cartridges to ensure efficiencies.
Okay. Under what conditions is this recommendable? For example, if you have 3 cents per kilowatt hour utility rate, it probably is not a good solution. Do you have any rules of thumb where it applies and where it does not?
Sure. So 3 cents per kilowatt hour is very, very low. Generally, most markets that are applying this as a retrofit are like 13 cents per kilowatt hour. Now, I will say this. Even in areas with very low cost of electricity, if it's a new construction project, you can see first cost capital savings and then ongoing maintenance savings, or at least net neutral versus the maintenance costs of cartridge changeout. So new construction, I'd say it's nationwide. Retrofit, you are going to want to be focused on utility rebates and high cost of electricity.
Okay, and do you have any kind of, let's assume there's no rebates, and let's assume, okay, I know it also matters, are you in the South where it's really hot, or are you in LA or Portland where it's not so hot, you're not going to save as much. But let's assume it's the southern band of the US. What rate do you need to pretty much make this be less than a 5-year payback?
Boy, it really varies. I'd say 8 cents and above. We're really active in the entire Northeast. We've got a lot of projects in the Northeast, all the way down the East Coast to Florida, then down through over across to Texas. Is all a great market for us. Colorado is great from an IQ perspective as well as first cost savings. And then we have great operations in Canada as well because of heating and cooling days there. So those are all hot markets for us right now.
Will it run without wireless? Because some facilities, they don't want that. Like some government facilities, they don't want wireless.
Yes.
That was easy. Good, thank you. Okay, here's one. The enVerid technical literature lists 2 different regeneration cycles per day. How many total times per day are the regenerative heaters running?
Yep, typically it's once a day for about an hour. It can be more, especially if there's full occupancy for the entire runtime. And the unit itself is able to figure out if cartridges are becoming saturated, but typically we're programming the system for once a day, worst case scenario, regeneration, and we can do a partial regeneration in the middle of the day or at the end of the day if the building was overly occupied.
Okay, and this may be our last one. At the University of Toronto, we burn natural gas to produce steam heat. Our main concern is CO2 production into the environment, right? We are mandated to reduce greenhouse gases, CO2. How does your unit address global CO2 increase?
Yeah, absolutely. I think I did a lunch and learn at the University of Toronto not too long ago with Adele and Associates, our representative up there in Ontario. Love it. We've got a lot of applications going on up there. Basically, our impact on global CO2 emission reductions is based on the energy that we're reducing in terms of the less runtime that you're seeing on heating and cooling applications. Unfortunately, we're not able to do much with the CO2 that we capture within the building, but where we're showing a significant carbon offset in production and where utilities are really behind us, and environmentally this is very good, is that you're seeing a 20 to 30% savings in terms of your HVAC runtime and how hard you're having to run those units because you're reconditioning already conditioned air as opposed to having to condition outside air.
That's it. We made it through all the questions, and we actually made it through all our time too. Do you have any final comments that you want to make before we wrap it up?
No, I threw my email address into the chat thread there. So if you have projects that are relevant, feel free to reach out to us. You can also email info@enverid.com. Really appreciate the opportunity. I know this is a new methodology for many folks, but it's doing the right thing for the planet. It's doing the right thing for indoor air quality. And we've had so much support over the past year. So for those of you who joined this webinar that I've met with already, I really appreciate you rejoining and supporting us. Abraxas, thank you so much. Congratulations on several years of doing these webinars, and thanks for the opportunity.